Alright, looks like we are live. Let's continue. Okay, let me open the table of content first. And okay, we are on chapter 19. And the last time is on the section 19.7, and now let's take a look at the summary here. 19.8. Let me open that. I think this one. Okay. Okay, the summary. We have seen how hardware can help us make address translation faster by providing a small, dedicated on-chip translation look-aside buffer as an address translation case. Most memory reference will hopefully be handled without having to access the page table in main memory. Thus, in the common case, the performance of the program will be almost as if memory isn't being virtualized at all. An excellent achievement for an operating system, and certainly essential to the use of paging in modern systems. Okay. The performance of the program will be almost as if memory isn't being virtualized at all. An excellent achievement for an operating system, and certainly essential to the use of paging in modern systems. However, translation look-aside buffer do not make the word rosy for every program that exists. In particular, if the number of bits a program accesses in a short period of time exceeds the number of bits that fit into the TLB, right, the program will generate a large number of translation look-aside buffer miss, and thus run quite a bit more slowly. We refer to this phenomenon as exceeding the TLB coverage. Oh, okay. And it can be quite a problem for certain programs. Wait a minute. Okay. One solution, as we will discuss in the next chapter, is to include support for larger page size by mapping key data structure into regions of the program's address space that are mapped by larger pages. The effective coverage of the TLB can be increased. Oh, okay. Exceeding the TLB coverage. Let me take note of that. Exceeding the coverage means that the number of pages that a program access or maybe process. Yeah, let's just use the program. Okay. That a program access in short period of time exceed the number of bits that fit into TLP. And the program will generate a lot of TLP miss. And the program will generate a lot of TLP miss and will be a bit slower. Okay, maybe something like this. Okay, one solution, as we will discuss in the next chapter, I'm assuming this one. Patching smaller tables. Okay, is to include support for larger page size. By mapping key data structure into region of the program address space that are mapped by larger page, the effective coverage of the TLP can be increased. Support for large page is often exploited by programs such as a database management system, DBMS, which have certain data structure that are both large and randomly accessed. Okay. One other TLP issue worth mentioning: TLP access can easily become a bottleneck in the CPU pipeline, in particular with what is called a physically indexed case. Become a bottleneck in the CPU pipeline. Physically indexed case. With such a case, address translation has to take place before the case is accessed. Which can slow things down quite a bit. Address. With such a case, this physically indexed case, address translation has to take place before the case is accessed, which can slow things down quite a bit. Because of this potential problem, people have looked into all sorts of clever ways to access case with virtual address, thus avoiding the expensive step of translation in the case of a cache hit. Such a virtually indexed case solves some performance problem, but introduce new issue into hardware design as well. See Wikin's Find survey for more detail. Okay, let's take a look at the reference here. Performance from architecture comparing a RISC and a CISC with similar hardware organization. Okay, a great and fair comparison between RISC and CISC. The bottom line, on similar hardware, RISC was about a factor of 3 better in performance. Oh, interesting. The evolution of RISC technology at IBM. A summary of the ideas and work behind the IBM 801, which many consider the first true RISC microprocessor. Okay, the core of the Black Canyon Computer Corporation. In this fascinating historical note, Collier talks about how he invented the TLP in 1964 while working for GE. What GE? This is the company name. Okay, and the fortuitous collaboration and thus fortuitous cooperation that thus ensue with the project MacFog at MIT. Okay, set access data processing system. The patent that contains the idea for an associative memory to store address translation. The idea, according to Collier, came in 1964. Okay. The architecture of the IBM system 370. Okay, perhaps the first paper to use the term translation look aside buffer. The name arises from the historical name for a case which was a look aside buffer ascribed by those developing the Atlas system at the University of Manchester. Wait, be right back. Bisa. Apa? Ya buat mana? Iya. Iya, siang tak makan lagi. Hello, I am back. Don't forget to drink water. Okay. The architecture of the IBM system 370. Perhaps the first paper to use the term translation look aside buffer. The name arises from the historical name for a case. Historical name for a case which was a look aside buffer as called by those developing the Atlas system at the University of Manchester. A case of address translation thus become a translation log asset buffer. Even though the term log asset buffer fell out of favor, TLB seemed to have stuck for whatever reason. Okay, so back then we call case as log asset buffer. Interesting. MIPS R4000 microprocessor user manual. Oh, this is the microprocessor. Okay, one that is surprisingly readable. Or is it? A manual. One that is surprisingly readable. Or is it? Okay. Computer architecture. A quantitative approach. A great book about computer architecture. We have a particular attachment to the classic first edition. Okay. Intel 64 and IA32 Architecture Software Developers Manual. In particular, pay attention to Volume 3A System Programming Guide Part 1 and Volume 3B System Programming Guide Part 2. Okay, RISC I guess a reduced instruction set VLSI computer. The paper that introduced the term RISC and start the avalanche of research to simplifying computer chips for performance. Wait a minute. Be right back again. It's been cold lately. Okay, the paper that introduced the term RISC and start the avalanche of research into simplifying computer chips for performance. Okay, CPU performance evaluation and execution time prediction using narrow spectrum benchmarking. Okay, a great dissertation about how to predict execution time of application by breaking them down into constituent piece and knowing the cost of each piece. Okay, probably the most interesting part that comes out of this work is the tool to measure the tail of the case hierarchy described in chapter 5. Case hierarchy, Oh, not chapter 5 this book. Yeah, I mean, okay. Chapter 5 in this dissertation, I guess. Make sure to check out the wonderful diagram therein. Okay. A survey on the interaction between casing. Survey on the interaction between casing, transition and protection. An excellent survey of how TLPs interact with other parts of the CPU pipeline, namely hardware case. Okay, survey of how TLP interact with other parts of the CPU pipeline, namely hardware case. Okay, the parts, architecture manual, another manual. I bet you were hoping for a more fun citation to end this chapter. You were hoping for a more fun citation to end this chapter. Okay. Let's continue into this section. Homework measurement. In this homework, you are to measure the size and cost of accessing a TLP. Oh, the idea is based on work by Saavedra Pereira. I probably pronounced that wrong. Okay, would develop a simple but beautiful method to measure numerous aspects of gate hierarchies, with a very simple user-level program. We develop a simple but beautiful method to measure numerous aspects of gate hierarchies, with a very simple user-level program. Read his work for more detail. SB92, where is it? I think this one. Okay. Interesting. The basic idea is to access some number of bits within a large data structure, for example an array. To access some number of bits within a large data structure, for example an array, and to time those access. For example, let's say the TLP size of a machine happen to be 4, which would be very small but useful for the purpose of this discussion. If we write a program that touches 4 or fewer bits, its access should be a TLP hit. 4 or fewer bits, its access should be a TLP hit, and thus relatively fast. However, once you touch 5 bits or more repeatedly in a loop, its access will suddenly jump in cost to that of a TLP miss. The basic code to loop through an array one should look like this. Okay. Numpage multiply jump. Okay. Then this one. Oh, plus equal jump. Alright. In this loop, one integer per base of the array is a. One integer per base of the array a is updated up to the number of bits specified by numpage, right? So I guess this is the offset, maybe something like that. Maybe. Okay. By timing such a loop repeatedly, say a few 100 million times in another loop around this world, or however many loops are needed to run for a few seconds, you can time how long each access takes on average. By looking for jump in cost as numpage increase, you can roughly determine how big the first level TLP is. Determine whether a second level TLP exists. A second level TLP exists. Oh. And how big it is if it does. And in general, get a good sense of how TLP hit and miss can affect performance. 19.5 Discovering TLP size and miss cost. Oh, okay. I'm assuming. Oh, this is time per access. I'm assuming the TLP size in this diagram is 4 according to this example. Okay. Figure 19.5 page 15, this one shows the average time per access as the number of page access in the loop is increased. Okay, figure 19.5 shows the average time per access as the number of page access in the loop is increased. The average time per access as the number of page access in the loop is increased. As you can see in the graph, when just a few pages are accessed, 8 or fewer, the average access time is roughly 5 nanoseconds. Okay, this is nanosecond time per access. Okay, what is the range here? our viewer, the flat access time is roughly 5 nanoseconds. Assume this one. When 16 or more pages are accessed, there is a sudden jump to about 20 nanoseconds per access. This one. Okay. Right. A final jump in cost occurs around 1024 pages, at which point its access takes around 70 nanoseconds. From this data, we can conclude that there is a two-level TLB hierarchy. The first is quite small, probably holding between 8 and 16 entries. The second is large but slower, holding roughly 512 entries. Oh, the jump is big. Okay. The overall difference between hits in the first level TLB and miss is quite large, roughly a factor of 14 TLB performance meter. Okay. Question: for timing, you will need to use a timer. Get time of day. I think I use different timer back then. Yeah, this is not the first homework measurement. We have another homework measurement previously. Where is it? On chapter 6 at least. So there is that. Yeah, if I remember correctly, I'm not using get time of day because it is deprecated, right? Yeah, I kind of forgot what did I use. Chapter 6 measurement. Oh, not this one. Cost of Siscal. Oh, I think this one. Oh, wait a minute. Or maybe this one, subtime spec. Oh. Okay, looks like I'm not using get time of day, but using clock get time. Be right back again. I am back. Okay. Clock at time. Okay, for timing, you will need to use a timer. How precise is such a timer? How long does an operation have to take in order for you to time it precisely? How long does an operation have to take in order for you to time it precisely? This would help determine how many times in a loop you'll have to repeat a batch access in order to time it successfully. I miss. Okay. This will help determine how many times in a loop you have to repeat batch access in order to time it successfully. Write a program called TLP.c that can roughly measure the cost of accessing each page. Input to the program should be the number of pages to touch and the number of trial. Now write a script in your favorite scripting language. Best to run this program while varying the number of bits accessed from one up to a few thousand, perhaps incrementing by a factor of 2 per iteration. Okay, run the script on different machine and gather some data. How many trials are needed to get reliable measurement? Okay. I am still not sure how we can measure the cost of accessing each page. Like, is it only accessing the variable like this? Okay. Next, grab the result, making a graph that looks similar to the one above. Use a good tool like Ploticus or Zplot. Visualization usually makes the data much easier to digest. Why do you think that is? Okay. Maybe because we can see the pattern easier when using visualization. Maybe. One thing to watch out for is compiler optimization. Compiler do all sorts of clever things, including removing loops, which increment values that no other part of the program subsequently use. How can you ensure the compiler does not remove the main loop above from your TLP size estimator? Okay, it looks like we can check that using this scenario. Plus equal 1, does that mean? We have what is it called? We have a initial value for each array because we are adding 1 there. Maybe okay. Another thing to watch out for is the fact that most systems today ship with multiple CPU, and each CPU, of course, has its own TLP hierarchy. Okay, to really get good measurement, you have to run your code on just one CPU instead of letting the scheduler bounce it from one CPU to the next. How can you do that? Look up finding a thread on Google for some clues. What will happen if you don't do this? And the code moves from one CPU to the other. I think I already tried that in this one, or maybe context switching. Yeah, maybe something like this. Sketch set affinity. Maybe. Oh. Yeah, I need to revisit that. Okay. Another issue that may arise relates to initialization. If you don't initialize the array A above before accessing it. Okay. The first, let me hide this. Wait a minute. Okay. The first time you access it will be very expensive. Due to initial access costs, such as daemon zeroing. Will this affect your code and its timing? What can you do to counterbalance this potential cost? Okay, so I assume we have two scenarios here. When not initialized array elements, and when initialized array elements, maybe something like that. Maybe let me create the directory first. This one is chapter 19. Oh yeah. Oh, they exist. Okay, right. I already have this info. Let me copy this here too. TLP.c. Okay. Input to the program should be okay. So we have input here, argument count and argument vector, I guess. Something like this. Oh, not this one. Is it? Yeah, I just want to make sure. Oh, bitrate example. Okay. Yeah. The, what is it called? Array of pointer, right? Okay. I mean, I can also do this, I guess, because the array decay into a pointer. But I feel like this is easier to understand. Okay. Hello, yes, Takur. Welcome. I also start going deep in process synchronization, especially semaphore. Oh, okay. I am still not sure what semaphore is. I mean, currently I'm still looking at the patching mechanism for the memory, I guess. So yeah, I haven't gotten into the semaphore. I assume it is from the concurrency. Maybe something like that. Yeah. But good luck to you, yes, Tukur. Okay, oh yeah, maybe this one. I haven't gotten into this one. I'm still in the virtualization here, the memory virtualization piece, right? From 3ECPs. Okay. Alright. Yeah, I'm kind of curious. Okay. And this. Pinning a thread. Well, let's continue all of this measurement question on the next session, I guess. So that's it for now. Thank you for watching and see you next time. Bye bye.